we were doing the change in exponential functions, we had made a table of data, x, and we decided to limit the area using this formula, the ratio of the growth rate and the area, limit area, added, multiplied with the previous term and the difference of the previous term to the limit added to the previous term. And then we took a logistic function. It looks like a logistic function, so we showed a regression. And if you show the regression, logistic with d equal to 0, here, there is this. Now, how do we solve for a ourselves? Well, we could choose a point that on the graph. Let me hide this regression. Choose a point, and 33, 34, 35, 36 is 627.175. And with that, I give the problem given 36, 627, and I could add more decimal place here to be more accurate, but basically I have to solve f of 36 equals 627 for a. Then I substitute, then I cross multiply, then I divide by 627, I subtract 1, and I divide by this expression here, because you are going to get this 1,000 multiplied by this whole thing. It's going to go here. And then the 1,000, this is 1 times 1,000, and that goes over here on this side. Then we're going to divide by the 627. So what remains is this, which is this. And then this, the 1 times 1,000 gets divided by the 627. Furthermore, I'm going to subtract this 1, so it no longer appears, and this is what we have. And over here it's subtracted, and then we have to divide by all of this expression here, exponential. So divide by that, and you end up with a equal to this whole thing divided by this, which is approximately 796. After I use a calculator to figure that out, I can copy and paste that result. This, Control C. Here, Control V. But it's not going to like this part, so let me Control X that. Back that up. And put this, and Control V, paste that little piece that was missing. Back up to parentheses. Doesn't like that. Maybe it doesn't like that. That's not really a division. So I'll put divide, and whoops, too many. And still doesn't look, oh, it's missing a parentheses. Okay. There. So just have to clean it up a little. So that is 796.82, which comparing that, 796. So comparing that with the one that was there, that had 740. So it depends what point you pick, but that's okay model. Okay, now today, let's move on to a different one. Let's save this. Control S, saving. And now, let's go to a new document, document 1. Add a spreadsheet this time. I'm going to save this as Villalobos, use your last name, 4.5. Title of this section is Exponential Growth and Decay. Okay, so Okay, so there you go. And this time, after we finish this relationship, we're able to write a function to represent a given situation, evaluate the function for given x, and solve the exponential equation in order to find values of x. Here's the exponential growth. Again, we have the general form y equals a times b to the x, where b is the growth factor, 1 plus or minus a rate, and a is the initial value. So again, this is the form. Oops. And this is the initial, oh my goodness. Initial value is a. Okay. Initial value, oh my goodness. So initial value is a and b is the growth factor. So b is greater than 1, it'll grow, b cannot be 0. If it's less than 1, then it will decay. Let's look. There's a social networking site. Every time it looks like row by row the membership started with initial value of 10, that's my A. Then each time it was 10 times 2. Then 10 times 2 itself was multiplied by 2, and 10 times 2 times 2 was multiplied by 2. So it looks like it's doubling each time. So here is our function. And to solve it, you just take the log of both sides and divide. So x is 4 divided by the log of 2. That's one way to explain it. So let's think about that. 13.3 is it the number of days it'll take to get to 10,000 members if you start with 10 and it's doubling by 2. So let's go here, and here's days, members, number of members, and we said at day 1 you had 10, and we said that this would be a 1 plus 1, and it was doubling. So this is actually just equal to, well, we already have a model, yeah? So what's our model? It's equal to A1, 10, the initial amount, times 2 raised to the power of A. So, but if you look at the table, it starts at 0, conveniently. So I need to put a 0 here. And then 1. This equals A1 plus 1. This would be a B1. This would equal B1 times 2. And I can highlight this, shift, and then up, then right, then control click, and we can do it for 7 days. Press enter. Sure enough, the model matches. But the question becomes, can I just calculate the time it'll take me to get to a certain number like 10,000? So I'm going to get to 100,000. So what does that look like? Insert calculator. 100, it's, so since logs are exponents, I need the log of the given base. I started out with 10, and I want to get to, I want to get to 100,000, starting with 10. And sure, it would take 4 days if the base was 10, but the base is not 10. base is 2, so I need to copy this, enter it, and change the base to 2. So it would be 13.28 or 13.3. Now in older calculators, yeah, I did have to do the log. You'd have to do the log in the base you're given, divided by the log you want, to change the base. That's called the change the base formula. Log of 2 is log base 10. So this is an alternate way to calculate the exponent that I would use to get the future value of 100,000 members, starting with the initial value of 10 members. And the algebra is as shown in the page. Okay, thank you. Let's pause for a moment, change problems. Here's another problem. In 1990, there was 20,000 in population, and in 2000, 10 years later, 35,000, and in 2010, 6125. Is this exponential growth? Well, according to the text here, you can assume that the initial population was 20,000, that's A, and that it was 1.75. And the question becomes, well, that's my function, when it's going to be a million, right? That's what they're asking in this question. So, you can solve the math like so, or let's think about it here. So you started with how many? Let's see. 20,000. 20,000 and growing 1.75. So you take the log, and you want to get to 1 million, that's 6 zeros. 3, 4, 5, 6, starting with 20,000. But not base 10. The actual base is 1.75. So in 6.99 years, that would be the answer if interpret that correctly. Let's see. Yeah, same result. Graphically, we can insert a graph. I know that -1. Click here until -1. And you're going to go to million. 1, 2, 3, 4, 5, 6. 1,000,001 maybe. Or 100. And then down here, at this number here, -1, 1, 2, 3, 4, 5. Let's maybe that's -1 is the -1, 1, 2, 3, 4. Okay, that's harder. Let's go menu, window, settings. Here's at -6, put it at -1, 1, 2, 3, 4. So maybe I can see a little bit better, but okay, there's this. And we're going to put in the function, which was 20,000 times 1.75 to the power of x, and tab ask for 1 followed by 6 zeros. No, not 6 zeros. One more zero. And apparently I put the window too high. One. Your E is located by your A, so that's E followed by 6 zeros. That would be the peak. And then I'm going to add just 5 zeros. 1, 2, 3, 4, 5. Just so I have some space. That's my intersection. So menu, analyze graph, find the intersection between here and here. And it's 2.88. So I must have this function wrong, because I think it was 20,000. I'm having 20 zeros. 20,000, there you go. And so the intersection is here. Trace, analyze graph, intersection, left, bound, right bound. And here's another way to do it. Now menu, settings, so that you can fix it. Float 3 to fix. If I can find fix. Fix 3 changes my display so it's after, it has 3 decimal places afterwards. So 6.999 is max. So basically 7, whatever that was, 7, what was the units did I write? 7 days? But this is the wrong model. 7 years. Right, it'll happen. So that's graphically and algebraically. How do you solve those? And remember the base we got from the table by simply dividing 35,000 divided by 20,000, just to see.